Hello, welcome to linear algebra. Today I'm going to be talking about the matrix equation AX equals B and independence. Last time we talked about span. To give you a brief reminder, span is the general concept of when you have some set of vectors, what is the shape of the space that they can define. So if you had two vectors here, say u and v, these could define everything in that flat plane here and extending in those directions. However, it does not cover any of the area along this axis here. Okay, that will tie into what we're talking about today, but for now, let's just dive into the matrix equation AX is equal to B. Start off with a definition. So this says, if A is an m by n matrix, so we have some matrix. So you can see what I'm writing on. Okay. We have some matrix, and it's size m, size n, with columns A1, A2, all the way to AN, and X is in some space Rn. Then the product of A and AX, denoted by AX, is the linear combination of the columns of A using the corresponding entries of X as the weights. That is, AX is equal to, these are the vectors, these are the coefficients or the weights, depending on which way you want to think about it. And then you can multiply them together. So that one times that one goes here. Next one goes here. And then so on, all the way down to the last goes here. This is exactly what we were talking about in previous lectures. So that's, you could rewrite this like this, where you have some AX, and instead of saying you have this right here, which is an equation, you could, if you substituted numbers in there, you could simplify that down to a single number, i.e. scalar. And you could represent that as a scalar right there. And I'm just choosing to call that one B. I mean, it's also the convention to call it B, but you could call it whatever you wanted. Okay. So actually, hold up. Let's do an example real quick. So example A not supposed to be anything here. I just made a mistake and I scribbled it out. These two, this matrix of coefficients and this vector are supposed to be right next to each other. Okay, so let's convert this into slightly different notation. Let me fix something in my notes real quick. Okay, there we go. So we can break this up into its constituent vectors and take the coefficient for each vector and put them together. So this corresponds to this vector right here. is how much this vector is scaled by. And then let's go for the next coefficient in the next vector. And then the next coefficient in the next vector. Okay. Now, using the properties that we know about scalars and vectors, let's rewrite this. And then simplify. So all the top elements together, and then all the bottom elements together. There you go, there's our resulting vector. Now, let's do a slightly more complicated version. I think we can fit it on this piece of paper. So the problem statement is, for V1, V2, V3 in Rm, write the linear combination of 3v1 minus 5v2 plus 7v3 as a matrix times a vector. Okay, so how we're going to do that is like this. So we have this equation here, and we can rewrite this as a matrix, so this set of vectors here. Set's probably not the right term. Set has a more specific meaning in math, and I am using it colloquially, which I probably shouldn't do. And then what we can do is we can just rename this A, and we can rename this X, and we can write that as AX. So this is our matrix, and this is our coefficient or weight vector. Now let's do the same thing, but with a system of linear equations. Okay, we've seen stuff like that before. Now let's write this in vector form. There we go. Then let's write this in matrix multiplied by vector form. And this is called a matrix equation. There we go. Cool. And this is in the form AX is equal to Another theorem. We're going to have a lot of them. A is an m by n matrix with columns a1 through an, so these are all vectors, and B, this is our scalar, is in Rm. The matrix equation A equals B, Ax equals B, has the same solution set as the vector equation x1a1 plus x2a2 through xn is equal to B. That makes sense from what we just saw. These two are equivalent, which in turn has the same solution set, so this and this has the same solution set as a system of linear equations whose augmented matrix is this. Okay, so when we were looking at the systems of equations earlier, and we were making augmented matrices, and we were reducing those in order to find the solution set to the system, we were using this form. What this says is they're all equal. This. That's pretty straightforward. The equation Ax equals B has a solution if and only if the B is a linear combination of the columns of A. So let's go back to thinking about span. If you have some space that looks like, where's the best place to put this? Yeah, new piece of paper. Okay, if we have some space that looks like this, and we have some plane coming through this space and it looks like this. All right, and let's say that this plane is constructed by this vector here, B, and this vector here, and this is going to be U. What this is asking is it possible for us to get to some point in this space, or some vector in this space, essentially the same thing, called B. So let's say B is in this plane, then we can use some multiples of U and V in order to get there, just like we saw last time, where you can add up multiples of U and V in order to span an entire plane. That's what we're asking here, is can we find this here using these combinations? Or alternatively, if B is off of this plane, can we get there? And the answer to that is no. We cannot get there if B is off the plane. So the equation Ax equals B has a solution if and only if the B is a linear combination of the columns of A. I hope that makes sense. If it doesn't, write me, and I'll do my best to clarify any confusion. Okay. Let's see, my next example. It's right here. Is B in the span A1 to AN? Equivalent question, is Ax equals B consistent? A harder problem to solve is to decide whether or not Ax equals B is consistent, i.e. has a solution for all possible B. Okay, so example. Let A equal a matrix, this matrix, and let B equal this set of coefficients. I really need to stop saying set. Is the equation AX equals B consistent for all possible B? I.e., does it have a solution? Is the B in the span generated by these vectors? Let's see. So first, let's make an augmented matrix. Cool. Seen stuff like that before. Then we go through all those steps shown previously to reduce this into as simple of a form as we can get it. So at first, this one's going to look a little different because we haven't done this with variables here before, but we're doing the same thing, except for every time we do it, the operations on this are not going to condense down to a single number because they're all variables. So we start seeing almost like a history of what we've done on the row operations shown in the variables in this last column, and you'll see what I mean in a second. Okay, so when they were doing all their operations on the rows of this, in order to simplify this down, evidently what they did is they added four times this row here. And for this one, we added 3 times the first row, and that allowed us to reduce down these. One thing I haven't mentioned that you'll need to know is that these entries, the leading entries in each row after the 0, so when it's reduced all the way, these leading entries are called pivot positions. That will come up later in some of our definitions. And it's important to know those because they help us see really easily which variables, so like if this is corresponding to x1, x2, x3, or rather in this case b1, b2, b3, whether or not there's going to be a non-zero solution for it in the final solution set. And that's important to know when we're thinking about independence and basis, which some of which we will get to later in this lecture. Okay, I drew this wrong because this is not big enough. So let's reduce this down even more. 1, 0, 0, 3, 14, 0, 4, 10, 0. So here we can see we don't have a pivot position here, which means that B3 is going to be a free variable. which means that we will be able to choose any number for B3, and it's going to be a valid choice, but we'll get there. B1, B2 plus 4B1, B3 plus 3B1 minus 1/2 B2 plus 4B1. Okay, so they took this and then subtracted half of that from it in order to reduce it all the way, if anyone was really curious about the real operations that they had done. Okay, so because for this last row, we don't have a pivot position here, the result when we simplify it down, so this last row will be B1 minus 1/2 B2 plus B3. Okay, so what that means is that this equation right here is something that allows us to solve for what values for these make the system consistent. So while there are a large set of values that could make the system consistent, it is not all values that can make this system consistent for each of these b. And since we have that last row of zeros in the row reduced echelon form, what that means is you can get a row of, you can put in a value for this last spot here where B3 was, but it was actually this in the reduced form, where this is equal to, say, 1. So it would be B1 minus 2, or sorry, 1/2 B2 plus B3 is equal to 1. And we know that this is not consistent, only this is consistent. So because of this, we know that the vectors in here do not span all Rm, because there exists values for B where this system is inconsistent. Okay. Let A be an m by n matrix, then the following statements are logically equivalent. That is, for a particular A, either they are all true statements or they are all false. So here's the first one. For each B in Rm, the equation Ax equals B has a solution. Okay. Each B in Rm is a linear combination of the columns of A. So these follow from the previous theorems that we've looked at. So we know that the equation Ax equals B is the same thing as the linear combination of the columns of A. So that makes sense for those to be equivalent. The columns of A span Rm. Okay. If the columns of A span Rn, there is no place for there to be a B that the linear combination of columns cannot reach. So therefore, there are no places that we could have an inconsistent system of linear equations for. A has a pivot position in every row. So this is getting back to the pivot position thing that I just introduced, where you have some matrix like this, and then you have pivot positions like this. These are pivot positions. And then you have some numbers here. What this means is that we will have set values for each of our variables here. And if we have set values for them, then what that means, and we'll be getting more into this later, is that there exists some set of vectors. These don't visually correspond to this, but let's pretend that they do, where this is vector 1, vector 2, vector 3, and among all of them, they will cover the entire possible space that is Rm. And then just note that the above, these statements are only true for a coefficient matrix like this. If you wanted to apply the same logic to an augmented matrix, which would be, let's say, like this, where this whole row of ones was equivalent to, like we had our system of linear equations, like this would be the other side of the equal sign. This does not hold true, just so you know. Just to submit at home how we can multiply a by x to get sum b. Okay. Let's see. So this is going to be expressed a little bit differently from the way we've seen it before. But it's not so different. So 2 times 4 plus negative 3 times 7, 8 times 4 plus 0 times 4. Sorry, 0 times 7. Negative 5 times 4 plus 2 times 7. And then this is going to be equal to negative 13. This is going to be equal to 32. And then this is going to be equal to negative 6. There you go. Okay, let's do one more, and let's do this one a little differently again. This matrix that I'm drawing right here is an important matrix, has a name. This is called the identity matrix, and it's called the identity matrix because, well, I can't say for sure because, but what it does do is it returns to you whatever you multiply on the right-hand side by it. So in this case, we can see that this is going to be 1 times r plus 0 times s plus 0 times t, then 0 times r plus 1 times s plus 0 times t, and then 0 times r plus 0 times s plus 1 times t. This is going to be equal to, okay, well, that all doesn't, it just becomes 0 So what we're left with is R, S, T, and that's what we got. Exactly as we expected. It is worth noting that the identity matrix is denoted by I. So whenever you see I, like you could see I times, B is not a good one, I times X is equal to X. There you go. And then some properties for you real quick. Just in writing, if that is something that's beneficial to you. If A is an m by n matrix and U and V are vectors in Rn, and C is a scalar, then these are the things we can do. So these are just algebraic properties for us, where I would think about this as distribution. I don't know if that is a term that can technically be used here, where you would multiply this and then multiply that to get here. And then for this, it doesn't matter if we have C multiplied by the vector first, or if we have the matrix multiplied by the vector and then multiplied by the scalar. And you can prove these to yourself if you would like to. Just express all of this in terms of, like for A, you could do, just make sure that your dimensions match up, otherwise it won't work. So say A1, A2, A3, A4, and then U is equal to U1 and U2. V is equal to V1, V2, and then C is just equal to C because it's a scalar. You could go through and prove all these to yourself using all of the previously expressed properties of algebra on vectors, scalars, and matrices. So we have a new term here. It's homogeneity. So a system of linear equations is homogeneous if AX, so just to scribble out, is equal to 0. So AX is equal to 0. This always has at least one solution where AX is equal to 0. So this is called the trivial solution. So, okay, if I have A and I multiply it by some 0 vector, and let's assume that A is 2 by 2 or 1 by 2. So let's say A looks like, let's say A looks like this, and we multiply it by 0, we will always get 0 out. And it's simply because everything on the inside is multiplied by 0, so when it gets added up, it equals 0. So for any matrix, if we multiply a vector by it that has the same number of columns that it has, we will always get 0. And this is called the trivial solution. If you ever hear the trivial solution in linear algebra contexts, just remember that it's not a judgment call on the difficulty of the problem. It's just a term, but it also happens to be fairly easy because it's pretty simple to see if you multiply everything in here by 0, that you're going to get out 0. Okay, let's do, or let's see, one second. Non-trivial solutions are non-zero solutions. So what that means is that at least one element in this vector is non-zero. So it could be I want to say for this, because this is our example of the trivial solutions. Let me grab a new piece of paper. So let's say we had some matrix like this, where these are vectors this time. Sorry, in my example over here, where I denoted these like this, these are intended to be elements, scalars, but often in the problems here, we use these to denote vectors. So this is going to be a vector. I'm sorry for being inconsistent here in my notation because it's going to be confusing. I will try to recall that a little bit better in the future. So these are vectors, and then if we had some other vector multiplied by this matrix, this is A right here, let's call this X, X1, X2. For the values in here, so long as any of those values is non-zero, even if it's like super small, it's still a non-trivial solution, so long as this is consistent. So let's do an example where there's a homogeneous system that has a non-trivial solution. Okay. So this is set to 0 because we're trying to verify and see if this has a solution, which is to say, are there values for these that make this equation true, or equal? So let's put this into our augmented matrix form. Okay, and then this eventually reduces down to this here. Okay, we can see that here there are no pivot positions, so we're going to have a free variable. Here we can see that we do have pivot positions, so those will be defined. Taking this into row reduced echelon form, all the way reduced, that is to say, we can see here that when we rewrite it as a system of equations, some of these things will be defined. Okay, so we have x2 is equal to 0. We have 1 depending on x3. x3 is undefined, which means that we are going to have not a single point that defines the system. We are going to have a line that defines the system. So let's figure out what that is. So let's say x is like this. Okay. Which is equal to, let's take out that x3. And we can rewrite this as x3 times a vector, where the vector is equal to that right there. Okay, what does that mean? Geometrically speaking, what that means is this. If we have some v in space, so say x1, x2, and x3, then I'm going to go over 4 over 3 on x1, go over nothing on x2, and then go up 1. Okay. This is going to be our v, and then we can scale it in either direction by x3, the variable x3 here. It's going to go here. Okay, and so this is going to be a line, and this line is the span of the vector v. Okay, and we can see that the solution to this set of linear equations can fall anywhere along this line. So if we have a b that occurs anywhere along this line, this system is going to be valid. So there you go. There's your example of a non-trivial solution in a homogeneous system. Let's do one more example. So let's say we have this system right here. Yeah, I know it's only one equation. Still counts as a system. It's just a very simple system. We can write this x again, like so. Okay, and this is going to be equal to x1 is equal to 0.3 x2 plus 2x3. So this is if we reduced everything down and then solved for x1 from here. And then x2 is equal to x2, x3 is equal to x3. And then if we broke this apart, into vectors, we would find 0.3 x2, x2 and 0, plus 0.2 x3, 0 and x3, which results in a system that has two free variables, and we could tell just from looking at this, based on the number of pivot positions we had. So if we wrote this as like a matrix, we could write that as 10, -3, 2, and then 0. This would be an augmented matrix for the system. We would only have one pivot position because there's only one row. We could only ever have one pivot position, which means that we would have to have two free variables. So there you go. That's a quick visual inspection. And what does this give us? This gives us geometrically so we could have this vector be called u, and this vector be called v. And those could fall in our space like this. So this would be u, this would be v. So you may see where I'm going with this already. This can now define a plane. So we see with two free variables that instead of a line, we now span a plane. So all of our solutions would then fall within that plane. And then let me draw this just a little bit better for us. So we can get a concept of the space that it is in. Well, that might not be better. That's okay. Good enough for now. If people come to me with questions, I will incorporate more examples into the next lecture so that I can make sure that that was well understood. But I think this is good enough for now. Okay, let's get into linear independence now. Oh wait, I missed some things. Let me cover it real quick. Okay, so the homogeneous equation ax equals 0 has a non-trivial solution if and only if the equation has at least one free variable. Let's take a look into why that's the case. So let's say we had all of our elements here, and then we had some x's here, and then we had it's equal to 0. Okay. So this 0 here is just the 0 vector, so it can be of arbitrary length. It's just easier to write like that. So let's write this out. x1 4x2 plus 3x3, and then x2 plus 2x3, and then x3. And then all of these are equal to 0. Well, okay, what happens then? So if x3 is equal to 0, let's substitute this into the above equations. Those reduce to x1, 4x2, and then, so if this is 0, 3 times 0 is 0, so it just cancels out, and then same thing here, and that just equals 0. And then we get x2 is equal to 0. Substitute into the above equation again, and you get this. So the result is the trivial solution if you don't have any free variables. And this isn't a rigorous proof by any means, but you get an idea of why that would be the case. Suppose the equation ax equals b is consistent for some given b, and let p be a solution. then the solution of ax equals b is a set of all vectors of the form w equals p plus vh, where vh is any solution to the homogeneous equation ax is equal to 0. So what this is showing here is that if ax is equal to 0 has some solution set that's a plane, this lower plane here, then for ax equals b, if b is not equal to 0, we are offset from this plane by some vector. Let's get into independence now. An index set of vectors v1 through vp in Rn is said to be linearly independent if the vector equation x1 v1 plus x2 v2 through xp vp is equal to 0. And that equation only has the trivial solution. The set v1 through vp is said to be linearly independent if there exist weights c1 through cp, not all 0, such that c1 v1 plus c2 v2 through cp vp is equal to 0. Okay, so what does linear dependence versus linear independence mean? If a vector is linearly dependent, it is a linear combination of other vectors. So a set of vectors that are all linearly independent are those where none of the vectors can be a linear combination of any of the others. And what this results to is when you add them all together, the only solution that you can get from them, if they're all linearly independent, is the trivial solution, is 0, where all the x's are equal to 0. And it's because there's no way of constructing a set of vectors where they will cancel each other out. So let's think about this graphically. So if you have a space like this, and again, let's go back to the example of a plane. So let's say you have some plane here, and let's say your vectors are here and here, and that these are both in this flat plane, like so. And you have another vector up here. Because of the solution set to this, just like with b, previously with ax equals b, there is no b that these vectors can get to. So there's no way we could add or subtract multiples of them in order to cancel out this one completely in all of its components. So in like the x1, x2, and x3 dimensions, you're still going to get, like, you could take out perhaps this distance here using some combination of these. But you could not remove this x3 component because these don't contain any x3 component. So the only way for them to completely cancel out is if you multiply each of these by 0. So in essence, you reduce the magnitude of them to the point in the origin. And so there's nothing really to add or subtract from them anyway. So like if you had some vector v1, some vector v2, and some vector v3, if you multiply them by 0, where this is x1, this is x2, and this is x3 right here, multiply them all by 0 and add them all together, well, they're just going to go to 0 in the first place, and so you're going to get 0 plus 0 plus 0 is equal to 0. And that's really what's meant by this here, but it's not immediately apparent. It's like, okay, well, you have some linear combination is equal to 0, and that's the only way they're independent. The reason why they're independent is because the whole point of talking about independence is whether or not, is determining whether or not every vector in the set of vectors that you're considering, in this case I do mean set, is not a linear combination of the others. So, and this can go beyond 3, of course. This is up to, in this case, p vectors. And then if you have a dependent vector, a dependent set of vectors, you only need one of them to be a combination of the multiples of the scalar multiples of the other vectors. And what does that mean? So if I took another vector and I just added it into this here, it would be like, let's say we aren't considering this one right now. We're only considering these two vectors down here. We would add in a vector here, and this vector is in the plane, which means that we can make a linear combination of, say, vector u and vector v in order to define that vector right there. And that would be a linearly dependent vector. Okay, let's do an example. So here we're going to be looking and seeing if the set of vectors v1 through v3 are independent. And we're going to check that by seeing if our matrix times our coefficients is equal to 0. So first we have to figure out what our coefficients are. And that would be, how we solve that is trying to find the solution set for our system. So let's write out our augmented matrix. And then this reduces here. And we can see right away from this that we're going to have 2 basic variables and 1 free variable, simply because of these pivot positions right here, and then this being a row of zeros. This reduced all the way down into row reduced echelon form is this. Okay, and we can rewrite that in equations like so. Okay, so there's our solution set. And okay, so we can rewrite this again like this. And then we could also rewrite this just as a note as 0 is equal to 0, which would be 0x3 is equal to 0, where this could be anything. Okay, now we could choose some values for this if we wanted to. we could stop here. But let's define the linear dependence relation for this system of linear equations by, okay, let's choose some value for x3. Let's say x3 is equal to 5. And then, okay, so that's going to be x2 is equal to negative x3, which is negative 5. And then x1 is going to be equal to 2 times x3, which is 10. And if we rewrote this, like our ax set of vectors, using these coefficients, what we would get would be 10 times v1 plus negative 5 v2 plus 5 v3 is equal to 0. There you go. There's your dependence relation. So it tells you how to scale those vectors in order to get 0, which is essentially telling you the linear combination of vectors that you would need in order to cancel them all out, which tells you that these vectors linearly depend on each other. They sit within each other's span. At least one of them sits within the other's span, and the scalar multiples of them can be used to cancel each other out, which means that they are not independent. Just doubly verifying that, even though we already knew that we had a solution that was not the trivial solution. We did not get all of these x's to be defined as 0. So we knew at that point that this was not going to be independent, but this elaborates on that for us. Okay. The columns of a matrix A are linearly independent if and only if the equation ax is 0 has only the trivial solution. We've covered this. We are familiar with it. We, I believe, understand why at this point, geometrically, and why in terms of this equation. This will just cement our understanding. Okay, so let's say we have vector 1 is equal to 3, 1, and we have vector 2 is equal to 6, 2. All right. Equal to, not multiplied by. Are these two vectors linearly independent? Okay. So let's take a look at them. When we look at these, we can start seeing vectors in terms of how much are they made up by this axis and this axis. So in this case, we have 3, so let's say this is 3, and this is 6, and let's say this is 1, and this is 2. So this is go over 3, up 1, there's our V1. But I can also immediately tell that V2 is going to be linearly dependent, and I can tell this because I can already see that it is a multiple of this. It's just the same thing multiplied by 2, which we can see overlaps perfectly on this to 6, 2. So V2 is equal to 2V1. Therefore, it's linearly dependent. Is this linearly dependent or independent? V1 is equal to 3, 2. V2 is equal to 6, 2. Well, is there a set of vectors, or sorry, is there a set of coefficients? Is there a vector? When multiplied by the matrix of these, that would be consistent, other than the trivial solution. Well, okay. First, let's look at it geometrically. So we have 1, 2, 3, 6, this is x1, x2, and then we have 1, 2. So we have this vector v1 is going to go here. And this vector v2 is going to go here. Is v2 or v1 a scalar multiple of the other? No, there is no scalar that I can choose that is going to make v1 into v2, because the span of v1 is along this line here, and the span of v2 is on this line here. Okay? So this is all the coefficients of v1, this is all the coefficients of v2. No matter what I multiply v1 by, I will never be able to find the address, essentially, of the point on v2 other than the origin. And this right here would just be the vector where the coefficients are equal to 0, which is the 0 vector, which is the trivial solution. So there are solutions other than the trivial solution. Sorry. There are not solutions other than the trivial solution, which means that these two are independent. And if you would like, go ahead and verify this for yourself using the procedure that I just showed, in the previous example. Okay. A set of two vectors, v1, v2, is linearly dependent if at least one of the vectors, a set of two vectors, v1, v2, is linearly dependent if at least one of the vectors is a multiple of the other. The set is linearly independent if and only if neither of the vectors is a multiple of the other. Okay, this is exactly what we just covered. So it's just formalized there if you would like to see it written out. Moving on. Characterization of linearly dependent sets. A index set S is equal to v1 through vp of two or more vectors if and only if at least one of the vectors S is a linear combination of the others. In fact, if S is linearly dependent and V does not equal 0, V1 does not equal 0, then some other V in the list, some Vj, with j greater than or equal to 1, so they're just saying any vector, not V1, is a linear combination of the preceding vectors. Okay, so this is just writing out what we just talked about. So in this case, you can see that the vector is in the span, vector W is in the span U and V, and here you can see that W is not in the span U and V, and therefore is linearly independent. And what this is saying is so long as one of those vectors in the set is a linear combination of the other vectors, it is not linearly independent. There you go. Okay. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent. That is, any set of vectors, v1 through vp, in Rn is linearly dependent if p is greater than n. Okay, so if we look at this sort of pseudo matrix-esque example down here where I've put in stars instead of entries in the matrix, elements in the matrix, you can see that we have a matrix that is wider than it is long. So what this is saying is we have, in this case, we have 5 vectors, and I've indicated if we were to have some coefficients for each of these, so x1 through x5. This is not saying what vectors they are, they'd be like vector 1 through vector 5, multiplied by the coefficients, which are the x's. Why would we not be able to have an independent set? Okay, so let's think about this in terms of pivot positions, or in terms of how many coefficients we could actually define here. So we would have 3 that we could define just because of the length, and then we would be forced to have 2 free variables. And because of that, we would have we could have values for these 2 variables that would not be 0. And because of that, we could not have the trivial solution, which would require all of these to be 0. So that way we could know for sure that this would have to be independent, or sorry, dependent, not independent. But we can also think about it a little bit differently. So let's say we had some space, and in this space, so each of these vectors exists in a 3-dimensional space. So actually in a 3-dimensional space here. So let's extract like this vector 1. So v1 is equal to this. Okay, so say this is x1, x2, x3. So we have some v1, and then we could put v2 and v3 in. But the max number of independent vectors we could have in this space is 3, because we're working in a 3-dimensional space. You know, we have we can only have so many different axes essentially, and in independences, we'll get more into for later videos. Each of these independent vectors can be thought of as its own axis. We could just, in essence, get rid of these axes, and these could function as new ones. But we can't have more than 3. So if we tried to add another one in, since these 3 vectors already span the entirety of this space, there's no points in here we couldn't get to. Any vector we add in is going to be a linear combination of the previous vectors, which means that the other vectors in this space are going to have to be linear combinations of the previous ones. So it can't be independent. All right. Our last one. If a set S is equal to V1 through Vp in Rn contains, so if the set contains a 0 vector, then the set is linearly dependent. Okay, so let's say we have 2 vectors, and I've just made up 2 vectors here. And we have them in some space here. Okay, so here's our vector 1 and our vector 2. I don't believe the graphic scales to the numbers here. And then we added in the 0 vector. So what is the 0 vector? So let's say we expressed our vectors like so. So we had the 0 vector, our vector 1, and our vector 2. So v1, v2, and 0 vector. And we added them all up, and equals 0. Why is this why is this dependent? So here's what the 0 vector is. We have our vector 1, our vector 2. The 0 vector, it has no length. Like, the length would be along x1, x2, x3, but it doesn't have any. It's just here. And so if we multiplied this or this by 0, we would get the 0 vector. So any vector ever is a linear combination of the 0 vector, because you can always construct it from it. So okay, let's say you have b1 is equal to 0, and you take b1 times v1 is equal to, in this case, 0 times 3 to 0 is equal to 0, 0, 0. There you go. The 0 vector is linearly dependent. It is within the span of v1, v2, or any v ever in real numbers. I cannot speak to imaginary numbers, but for real numbers I can say this is the case. Okay, I'm gonna have to stop there because my voice is giving out. But there you go. I hope that was helpful. Please write me if you have any questions. As part of the Discord space, I'm always available. So let me know if there's anything I can clarify. And thank you for watching.